On the 11th of March, 2011, a fault line beneath the Pacific Ocean off the coast of Japan finally gave way after building pressure for centuries, unleashing one of the most powerful earthquakes ever recorded. And when researchers went back afterward to check exactly when it struck against the pull of the moon, they found something that made more than one of them go quiet for a moment. It had ruptured almost precisely when the tidal stress on that fault was near its peak. Welcome to pale blue drift. For more than a century, scientists have argued over a question that sounds, on its surface, almost too strange to be real. Does the moon, hanging quietly overhead every night, tugging gently at the oceans below it, also reach down into solid rock and nudge fault lines closer to failure? The idea is called tidal triggering, and for most of that century it has lived in a frustrating kind of scientific limbo, dismissed by one study, cautiously supported by the next, never quite settled either way. But in recent years, a handful of researchers going back through the largest earthquakes in modern history have started finding a pattern too consistent to easily wave away, and it has reopened a question many scientists assumed had already been closed. The idea itself is not new, and it is not, once you understand the mechanics, particularly outlandish. The moon's gravity does not only pull on water, it pulls on the solid body of the Earth as well, flexing the crust itself by a small but measurable amount twice a day, the same rhythm responsible for the rise and fall of ocean tides along every coastline on the planet. This flexing, known as the solid Earth tide, applies a gentle, rhythmic stress to rock everywhere on the planet, including rock sitting along fault lines already under enormous tectonic pressure, slowly building toward their own eventual rupture over years or centuries. The physical reasoning is straightforward enough. If a fault is already stressed close to its breaking point, even a small additional nudge, arriving at exactly the wrong moment, could theoretically be enough to tip it over the edge. For decades, though, when scientists actually went looking for this effect in real earthquake data, the results kept coming back frustratingly mixed. Some studies, focused on specific regions or specific types of faults, found modest but real statistical evidence that earthquakes were slightly more likely to occur near the peak of tidal stress. Other studies, run on different data sets using different statistical methods, found nothing conclusive at all, no meaningful pattern distinguishing tidal peaks from any other random moment. Entire academic careers were built quietly around this puzzle, researchers publishing papers on both sides of the argument, each one adding another layer of data without ever quite resolving the underlying question. Part of the difficulty came down to something deceptively simple. Small earthquakes, the overwhelming majority of seismic events recorded anywhere on the planet, occur along faults that may not yet be close enough to their own breaking point for a small tidal nudge to make any real difference. If a fault has years left before it naturally reaches failure, a tiny twice-daily stress fluctuation from the moon's pull is unlikely to change much of anything about its timing. But researchers began to wonder whether the story might look different for a much rarer category of event, the largest earthquakes on the planet, the ones capable of leveling cities and triggering tsunamis, precisely because faults capable of producing ruptures that large are, almost by definition, already sitting right at the edge of failure by the time they finally let go. That is exactly the question a team of Japanese researchers set out to answer in the years following the 2011 Tohoku earthquake, and their approach was refreshingly direct. Rather than looking at every earthquake ever recorded, a dataset so enormous and varied that meaningful patterns tend to drown in statistical noise, they focused specifically on the very largest earthquakes in the modern record, ruptures with a magnitude of 8 or higher, the rare handful of events capable of reshaping coastlines and altering the length of the Earth's day by fractions of a second. When they calculated the tidal stress acting on each of those fault lines at the precise moment each earthquake struck, a pattern began to emerge that was difficult to dismiss as coincidence. The Tohoku earthquake itself, along with the devastating 2010 earthquake in Chile and the catastrophic 2004 earthquake off the coast of Sumatra, one of the deadliest natural disasters in modern history, had all ruptured during periods when the tidal stress on their respective faults was climbing toward, or sitting near, its highest point in the tidal cycle. Statistically, the researchers found that the largest earthquakes in their dataset showed a meaningfully higher tendency to occur near tidal stress peaks than would be expected if timing were simply random, a pattern that grew stronger, not weaker, as they restricted their analysis specifically to the most powerful events on record. Their proposed explanation reached back to the basic physics of how a rupture actually grows once it begins. Every large earthquake starts as a small one, a tiny initial slip along some point on a fault, which then either dies out harmlessly within moments or continues expanding outward into neighboring sections of the fault, feeding on the stress already stored there, eventually cascading into something far larger. The researchers proposed that additional tidal stress, arriving at exactly the wrong moment, might not be what starts an earthquake in the first place, but could instead influence whether an already initiated small rupture continues expanding into something catastrophic, tipping the odds slightly in favor of a minor slip, cascading into a major one, rather than fizzling out on its own the way the vast majority of small ruptures ultimately do. This distinction matters enormously, and it is worth sitting with for a moment, because it reframes the entire question in a way that finally makes sense of decades of frustratingly mixed results. If tidal forces mainly influence whether a rupture already underway continues growing, rather than whether an earthquake starts in the first place, then searching for a tidal pattern across all earthquakes indiscriminately, most of which never grow large enough for the effect to matter, would understandably produce weak, inconsistent results. But narrowing the search specifically to the rare giants, the earthquakes that did grow into catastrophic events, is exactly where a real signal would be expected to hide, and that is precisely where these researchers finally found one. News of the finding spread quickly through the seismology community, and reactions were, appropriately, a careful mixture of genuine excitement and immediate scrutiny. A correlation between the largest earthquakes in the modern record and the timing of tidal stress peaks is a striking result, but striking results in a field this contentious tend to draw exactly the kind of rigorous, skeptical review they deserve. Other researchers began independently re-examining the same dataset, checking whether the pattern held up under different statistical assumptions, whether it could be explained by some other coincidental factor tied to when and where major earthquakes happen to occur, whether the sample size, a relatively small handful of magnitude 8+ events across the available historical record, was large enough to draw a truly reliable conclusion from it all. This is precisely the kind of careful, adversarial testing that any genuinely important finding in science has to survive, and years later, the debate remains, in the most honest sense, unresolved but newly energized. The correlation identified in this specific handful of enormous earthquakes has held up reasonably well under continued scrutiny, encouraging enough that researchers have expanded their search into other categories of seismic activity entirely, including a much stranger and more subtle phenomenon known as slow slip, a gentle, drawn-out kind of fault movement that unfolds over days or weeks rather than the sudden violent seconds of an ordinary earthquake. Too gradual to ever be felt by anyone standing above it, but detectable through sensitive instruments monitoring the ground continuously over time. Slow slip events turn out to be a particularly interesting place to search for tidal influence, precisely because they unfold gradually enough that a small periodic nudge has more opportunity to actually shape their behavior, compared to an ordinary earthquake that ruptures and finishes within seconds. Recent theoretical work modeling exactly how a fault already sliding slowly and stably might respond to a repeating tidal stress has shown that even quite small periodic perturbations can meaningfully influence the timing and pace of these slow-moving events. sometimes locking their rhythm into step with the tidal cycle itself, sometimes pushing them from a smooth, gradual slip into a faster, more complex pattern of movement. This theoretical framework offers, for the first time, a plausible physical mechanism explaining not just whether tides might matter, but specifically how and where in the enormous spectrum of fault behavior their influence should be strongest. A level of specificity the field has been reaching for since researchers first proposed the basic idea more than a century ago. There is another place entirely, far from any ocean, where this same underlying idea has already moved past debate and into settled scientific fact, and it comes from somewhere far quieter than Earth altogether. Deep beneath the surface of the moon itself, seismometers left behind decades ago by astronauts recorded a category of tremor scientists called deep moonquakes, tiny shifts occurring hundreds of miles below the lunar surface. And when researchers went back through those decades-old recordings, they found something almost too clean to be a coincidence. The timing of those moonquakes lines up closely, and repeatedly, with the tidal stress the moon experiences as it orbits the Earth, stress considerably stronger, relative to the moon's much smaller size and lack of any ocean to absorb it, than anything Earth itself experiences from the moon's pull in return. On the moon, tidal triggering of seismic activity is not a contested hypothesis anymore. It is an accepted, well-documented feature of how that small, airless world quietly shudders in rhythm with its own orbit. That settled lunar evidence has become an important piece of context for researchers studying the far messier, far more contested question back here on Earth, a reminder that the basic physics underlying tidal triggering is entirely sound, proven beyond doubt on a smaller, simpler world next door, even while the specific conditions required for that same physics to meaningfully shape an earthquake's timing here on our own, far more geologically complicated planet remain an active, unfolding area of careful, ongoing research. Tonight, in seismology departments scattered across the globe, that research continues quietly, researchers running fresh statistical tests against newly logged earthquakes, checking each new major rupture against the tidal stress acting on its fault at the moment it finally gave way, slowly adding one more data point to a puzzle that has occupied some of the most careful minds in the field for well over 100 years. Still not fully solved, but closer in recent years to a real answer than at any point since the question was first seriously asked. That question of slow, drawn-out fault movement is exactly where some of the clearest evidence for tidal influence on Earth has actually turned up, and it comes from a stretch of coastline running along the Pacific Northwest, buried far too deep to ever be felt by anyone living above it, discovered almost by accident by researchers who were not initially looking for anything related to the moon at all. Beneath the coast of British Columbia and Washington state sits a subduction zone called Cascadia, where one of the Earth's tectonic plates is slowly forced beneath another, grinding downward at a pace of only a few centimeters each year, a motion so gradual it would be entirely invisible without extremely sensitive instruments to detect it. In the late 1990s and early 2000s, researchers monitoring this region with continuous GPS stations began noticing something strange in the data, a segment of the fault that periodically reversed its usual direction of slow, steady creep, moving backward briefly every so often before returning to its normal pace, a pattern nobody had ever documented in a subduction zone before. Around the same time, a separate network of seismometers listening for ordinary earthquakes in the same region began picking up something else entirely, a faint, continuous rumble too weak and too smeared out in time to register as a real earthquake, more like a persistent hum buried deep in the noise floor of the instruments. For a while, these two observations, the revering GPS movement and the strange seismic hum, were studied by entirely separate groups of researchers who had no immediate reason to connect them. It was only when scientists began comparing the timing of both signals directly that they realized something remarkable. The strange hum and the revering ground movement were happening at exactly the same time, in exactly the same place, again and again, on a cycle repeating roughly every 14 months. Researchers named this newly discovered phenomenon episodic tremor and slip, and it fundamentally changed how seismologists think about how tectonic plates actually move against each other. Rather than assuming plates simply lock together and then release all at once in a sudden, violent earthquake, or otherwise creep along smoothly and continuously, Cascadia revealed a third category of behavior entirely, a fault segment that mostly stays locked, then periodically slips gently and quietly over the course of several weeks, releasing a portion of its accumulated stress not through a dramatic rupture, but through a slow, silent, months-long exhale, accompanied by that same faint, sustained tremor the entire time. Once researchers understood what they were looking at, an obvious question followed almost immediately. Did the precise timing of that tremor, hour by hour, correlate in any way with the rhythm of the tides? And when they went back and checked, carefully, hour by hour, against the tidal stress acting on that specific fault segment, the correlation turned out to be startlingly clear, clearer, in fact, than almost any tidal correlation ever documented for an ordinary earthquake anywhere else on the planet. Tremor activity along the Cascadia Fault consistently intensified during specific phases of the tidal cycle, weakened during others, tracking the rhythm of the tides closely enough that researchers could use tidal timing itself to help predict which hours during an active slip episode were most likely to produce a burst of tremor. This finding mattered enormously for the broader tidal triggering debate, because it offered something the field had been missing for a century, a category of fault behavior where the tidal signal was not buried in statistical noise, requiring painstaking analysis across thousands of events just to detect a faint pattern, but instead stood out clearly, robustly, in nearly every single slip episode researchers examined. Similar tremor and slip behavior, once scientists knew specifically what signature to search for, was subsequently identified along other subduction zones and fault systems around the world, including a well-studied segment of the San Andreas Fault in California, where deep, non-volcanic tremor was likewise found to track tidal stress with a clarity that ordinary shallow earthquakes almost never display. The emerging explanation for why this particular category of fault behavior responds so cleanly to tidal forces, where ordinary earthquakes mostly do not, comes back to the same underlying physics researchers had already proposed for the largest earthquakes on record. These slow slip zones sit in a genuinely unusual mechanical state, neither fully locked and rigid the way most of a fault typically behaves, nor freely sliding the way rock deep in the Earth's plastic, flowing mantle does. They exist in a delicate in-between condition, close enough to the edge of slipping that a small periodic nudge, arriving in rhythm with the tides, is enough to meaningfully influence exactly when that slip actually occurs, without needing anywhere near the enormous stress required to trigger an ordinary sudden earthquake on a more rigidly locked stretch of fault. This gave researchers something they had lacked for the entirety of the 20th century, a specific, testable prediction about exactly where tidal triggering should be strongest, and it held up remarkably well as more subduction zones and slow slip regions were studied around the world. Rather than treating tidal triggering as a single, uniform question applying equally everywhere, the field began understanding it as something closer to a spectrum, faint and difficult to detect in most ordinary shallow crustal earthquakes, strikingly clear in slow slip and tremor zones, and, as the largest earthquake analysis had separately suggested, meaningfully present specifically in the very largest, most catastrophic ruptures on record. That refined understanding did not end the skepticism surrounding this field, and it would be dishonest to suggest otherwise. Plenty of careful, well-respected seismologists remain genuinely unconvinced that tidal forces play any meaningful role in most earthquakes people actually experience, the small to moderate events that make up the overwhelming majority of seismic activity worldwide. Several large-scale statistical studies, examining enormous global earthquake catalogs containing hundreds of thousands of individual events, have found no reliable overall increase in ordinary earthquake activity during periods of peak tidal stress, a result that stands in direct tension with the more targeted findings researchers have documented specifically among the largest earthquakes and slow slip zones. Reconciling these seemingly contradictory results has become one of the more interesting ongoing conversations within the field, and the leading explanation researchers currently favor is not that either set of findings is simply wrong, but that tidal triggering genuinely is not a uniform, universal effect applying equally to every category of seismic activity. It appears to matter considerably more for the rare, catastrophic ruptures capable of cascading across enormous sections of fault, and for slow slip zones sitting in that delicate, near-critical mechanical balance, while remaining essentially undetectable amid the much larger, noisier population of ordinary small and moderate earthquakes occurring on faults that are simply not yet close enough to their own breaking point for a small tidal nudge to matter at all. There is a particular study, focused on a specific stretch of active fault running beneath Greece, that illustrates this nuance especially well. Researchers examining decades of seismic records in that region found a genuinely striking pattern, earthquakes becoming meaningfully more likely during specific portions of the combined solar and lunar tidal cycle, a correlation strong enough that seismologists studying entirely different regions took notice, wondering whether Greece's particular geology, sitting at a complex junction of colliding tectonic plates, might make it an unusually sensitive natural laboratory for detecting an effect that remains far more subtle almost everywhere else. That specific correlation does not, on its own, prove tidal forces are meaningfully triggering earthquakes worldwide. But it adds another regional case where the effect appears clear enough to study in detail, joining Cascadia, the San Andreas tremor zones, and the statistical pattern found among the largest earthquakes in the modern record, each one a separate thread in a slowly tightening, still incomplete picture. What all of this means, practically, for anyone hopping tidal patterns might one day help forecast earthquakes before they happen, is a question researchers answer with real, careful caution. Even in the clearest cases, Cascadia's tremor and slip cycle, or the correlation found among the largest earthquakes in history, tidal stress functions as an influence on timing, nudging the odds slightly, rather than as a switch capable of triggering an earthquake on a fault that isn't already close to failure regardless. A fault sitting years away from naturally reaching its breaking point will not suddenly rupture because the moon happens to be full. What tidal forces appear to do, in the specific situations where the evidence is strongest, is shift the exact moment of failure earlier or later by hours or days, for a fault that was, in nearly every case, already destined to fail sometime relatively soon regardless of the moon's position that particular night. That distinction is exactly why no seismologist currently working in this field is proposing that tidal forecasting could ever replace the kind of long-term earthquake hazard modeling already used to estimate risk in earthquake-prone regions around the world. But it does suggest something genuinely valuable for a much narrower, more technical purpose, refining the odds within an already identified high-risk window. If a fault is independently known, through other lines of geological evidence, to be approaching the end of its typical rupture cycle, understanding its specific relationship to tidal stress could, in principle, help researchers identify which particular days or weeks within that broader window of elevated risk deserve the closest attention, a genuinely useful, if modest, addition to the much larger toolkit already used for earthquake hazard assessment. Research along these lines continues actively today, spread across seismology departments on nearly every continent. Some teams refining the statistical methods used to detect tidal correlations in increasingly large earthquake catalogs, others deploying new, more sensitive instrumentation specifically into known slow slip zones to capture the relationship between tremor and tidal stress in ever finer detail. Still others working through the theoretical physics of exactly how a fault's frictional properties determine whether it responds to a tidal nudge at all. To really appreciate how far this field has come, it helps to go back to where the question actually began, more than 100 years before Cascadia's tremor was ever discovered, in an era when scientists barely had the instruments necessary to even measure an earthquake precisely, let alone compare its exact timing against the subtle mathematics of tidal forces. In the final years of the 1800s, a physicist studying statistics noticed something that struck him as worth investigating further: a rough tendency for earthquakes in certain regions to cluster slightly more often around the times of new and full moons, the 2 points in the lunar cycle when the sun and moon's gravitational pulls align most directly, producing the strongest combined tidal stress of the entire month. It was a modest, uncertain observation, based on data crude by modern standards, but it planted a question that would occupy the field for more than a century afterward, refusing to be either conclusively proven or conclusively dismissed, no matter how many researchers eventually took it up. For most of the 20th century, that refusal to settle cleanly in either direction became almost a running theme within seismology itself. Study after study emerged, each one examining a different region, a different earthquake catalog, a different statistical method, and each one arriving at its own answer, some finding a small but real correlation, others finding nothing distinguishable from pure chance. By the 1980s, enough contradictory results had piled up that many seismologists had grown genuinely skeptical the effect was real at all, suspecting that whatever positive correlations had been reported likely reflected statistical noise, or subtle flaws in how researchers had selected and filtered their earthquake catalogs, rather than any genuine physical influence from the moon and sun reaching down into the Earth's crust. What eventually revived serious interest in the question, decades later, was not a single new discovery so much as a shift in how researchers approached the problem entirely. Rather than searching broadly across every earthquake in a massive, undifferentiated catalog, hoping a faint universal signal might somehow emerge from the noise, researchers increasingly began narrowing their focus deliberately towards specific categories of seismic behavior where the underlying physics gave good theoretical reason to expect tidal influence might actually be detectable, the very largest earthquakes. Specific fault types like shallow thrust faults where the geometry made tidal stress especially relevant, and eventually, the newly discovered slow slip and tremor zones that turned out to display the clearest correlation of all. This shift in strategy mirrors something that shows up repeatedly throughout the history of science: the recognition that a real, genuine effect can remain stubbornly invisible for a century, not because it isn't there, but because researchers were searching for it in the wrong place, averaged across too broad and too noisy a dataset to ever reveal itself clearly. Narrowing the search, guided by an increasingly refined theoretical understanding of exactly where and why the effect should be strongest, is precisely what finally allowed a century-old, frequently dismissed hypothesis to accumulate the kind of consistent, repeatable evidence capable of genuinely shifting scientific opinion. There is one more corner of this story worth exploring before we let it rest completely, because it involves not earthquakes along ordinary tectonic faults, but a very different, equally patient kind of geological rhythm, found along the volcanic ridges running beneath the world's oceans, deep beneath the sea. Stretching for tens of thousands of miles across every major ocean basin, sit mid-ocean ridges, enormous volcanic mountain chains where new oceanic crust is constantly being formed as tectonic plates slowly pull apart from each other, magma rising continuously to fill the gap left behind. These ridges experience their own near-constant seismic activity, small earthquakes and volcanic tremor accompanying the slow, patient process of new seafloor being born. Researchers studying seismometers placed directly on the ocean floor near several of these ridges found something that, in hindsight, makes a great deal of physical sense, even though it surprised many scientists when it was first documented clearly. Seismic activity along these underwater volcanic ridges correlates with the tidal cycle far more strongly and far more consistently than earthquakes along ordinary continental faults do. The leading explanation connects directly back to the unusual load-bearing role that ocean water itself plays in this specific environment. The rise and fall of the tide does not only flex the solid rock of the seafloor, the way Earth tides flex continental rock everywhere on the planet. It also adds and removes an enormous, genuinely significant weight of ocean water directly above these ridges twice a day, a load large enough to measurably affect the pressure acting on magma chambers and fracture networks sitting just beneath the seafloor. This additional, water-driven component of tidal stress appears to interact particularly well with the shallow, magma-weakened rock found along these spreading ridges, rock that is often close to the surface, hot, and mechanically far more sensitive to small pressure changes than the deeply buried, rigid rock typically found along inland continental faults. Researchers studying eruptions and seismic swarms along several well-monitored underwater ridges have found tidal correlations clear enough to be genuinely useful for understanding the detailed mechanics of how these volcanic systems behave, adding yet another environment, alongside the largest continental earthquakes and the slow slip tremor zones, where the moon's gentle, twice-daily pull on the Earth appears to leave a real, measurable fingerprint on when and how the ground beneath us actually moves. Taken together, these separate threads, the century-old statistical puzzle first noticed before anyone had modern seismometers, the large earthquake correlation identified only after Tohoku forced researchers to look more carefully, the strikingly clear tremor and slip cycles discovered almost by accident beneath Cascadia, and the volcanic ridges where an entirely different, water-driven mechanism produces its own distinct tidal signature, paint a picture considerably more nuanced and considerably more interesting than either a simple yes or a simple no could ever capture. There is a quiet kind of humility built into this entire 100-year investigation that is worth sitting with for a moment before we move on. Generations of careful, well-trained scientists have devoted real portions of their careers to a question that, for most of that century, seemed destined to end in nothing. A hypothesis proposed, tested, found wanting, and set aside, only for the next generation of researchers to pick it back up with sharper tools and a slightly different question, patient enough to keep refining an idea that could easily have been abandoned outright after so many inconclusive results. That patience is precisely what eventually allowed the signal to emerge from Cascadia's tremor, from the statistics of the largest earthquakes on record, from the volcanic ridges hidden beneath miles of seawater. None of it happened quickly. All of it required exactly the kind of quiet, unglamorous persistence that rarely makes headlines on its own, but which slowly, patiently, builds the foundation every genuine scientific understanding eventually rests upon. The moon does appear to reach down and touch the solid Earth in ways that measurably influence seismic activity, but only in specific, carefully identified circumstances, where a fault or magma system already sits close enough to its own breaking point that a small, rhythmic nudge arriving on schedule every 12 hours is enough to matter. It remains, after more than 100 years, one of the quieter, more patient ongoing investigations in all of Earth science, a slow, careful accumulation of evidence toward a question that sounds almost too strange to take seriously at first. Whether the same gentle gravitational pull responsible for the tide rising along your nearest coastline tonight might also, in certain very specific circumstances, be reaching down into solid rock deep underground, nudging some of the largest forces on the entire planet by just enough to matter. That kind of patient, decades-long persistence eventually led researchers somewhere genuinely practical, past pure statistical correlation, and into an actual attempt to test whether tidal stress could be built directly into a working forecast. And the region chosen for that test sits along one of the most closely watched and most consequential subduction zones on the entire planet. The same stretch of coastline off Japan that had already forced the field to take this question seriously in the first place. In the years following the Tohoku disaster, Japanese seismologists faced enormous public and scientific pressure to improve earthquake forecasting along their coastline, and a portion of that renewed effort turned directly toward the tidal correlation researchers had identified in the largest earthquakes on record. Rather than treating tidal stress as an interesting statistical footnote, several research teams began incorporating it directly into probabilistic models designed to estimate, hour by hour, the relative likelihood of a major rupture occurring along specific monitored fault segments. The approach was deliberately modest in its ambitions. Nobody involved was claiming the ability to predict a specific earthquake on a specific day. Instead, the goal was to slightly refine an already existing hazard estimate, nudging the probability up during hours of peak tidal stress and down during hours of minimum stress. A small adjustment layered on top of far larger, more established methods already used to estimate long-term earthquake risk. Testing a forecasting method like this rigorously requires an enormous amount of patience, because a fair evaluation demands wading through many actual earthquakes, comparing how often ruptures occurred during the hours the model flagged as elevated risk versus the hours it flagged as lower risk, repeated across enough events for the results to mean something statistically. Early results, drawn from a still relatively modest number of qualifying large earthquakes, have shown a modest but genuine tendency for major ruptures to cluster somewhat more often during the specific windows the tidal models flagged as elevated, an encouraging sign for researchers, though still far too limited a sample to consider the method fully validated or ready for any kind of practical, public-facing use. This cautious, incremental progress captures something important about how genuine scientific advancement in a field this difficult actually tends to unfold in small, well-documented steps, each one openly acknowledging its own limitations, rather than in the sudden, triumphant breakthroughs that dramatic retellings sometimes prefer. Researchers working on these tidal forecasting models are notably careful, in every published paper and every public statement, to stress precisely what the method can and cannot do. It cannot tell you an earthquake will strike on a specific date. It cannot identify which particular fault, among the countless fault segments crisscrossing a seismically active region, is actually approaching failure at any given moment. What it can potentially offer, if the ongoing testing continues to hold up, is a modest refinement layered on top of independently established, long-term hazard assessments already built through decades of geological mapping, historical earthquake records, and detailed stress modeling of specific known fault segments. That last detail matters enormously, and it is worth returning to directly, because it addresses the single most common misunderstanding that tends to surround this entire field whenever it reaches a wider audience. Tidal forecasting research is not, and has never been, an attempt to predict earthquakes out of nothing, plucking a random date from the calendar based purely on when the moon happens to be full or new. It only becomes potentially useful specifically for fault segments that geologists have already identified, through entirely separate lines of evidence, as approaching the natural end of their typical rupture cycle, based on decades of accumulated strain, historical recurrence intervals, and detailed measurements of how much stress has built up since the fault's last major rupture. Within that already narrowed window of elevated background risk, which might span years or even decades depending on the specific fault, tidal stress offers, at best, a modest tool for further narrowing which particular days or weeks within that broader window carry marginally higher risk than others. It is worth being honest, too, about the considerable skepticism that continues to surround even this narrower, more carefully bounded application. Some researchers, deeply familiar with the long, frustrating history of failed earthquake prediction claims throughout the 20th century, remain genuinely concerned that even a cautiously framed tidal forecasting method risks being misunderstood or oversold once it reaches a public audience less familiar with the careful statistical language researchers use internally. Earthquake prediction, in the broad public sense of confidently naming a specific date, time, and location before an earthquake strikes, has an extraordinarily poor track record throughout the history of seismology, littered with false alarms, discredited methods, and no shortage of confident predictions that never came true, alongside real earthquakes that struck without any warning at all from methods that claimed to be reliable. That difficult history has left many careful scientists deliberately cautious about associating their own more modest, statistically framed research with anything resembling a public prediction, even when the underlying science genuinely does show a real, if limited, correlation. This tension between genuinely interesting, statistically real findings and the very real risk of those findings being misrepresented as something far more definitive than they actually are, sits at the heart of nearly every conversation happening within this field right now. Researchers publishing new tidal correlation studies routinely include extensive caveats directly in their papers, specifying exactly how modest the effect size actually is, how narrow the specific circumstances are where it has been reliably documented, and how much additional research remains necessary before any of it could responsibly inform public-facing hazard communication in any meaningful way. That careful, repeated emphasis on limitation is not a sign of weak science. It is, if anything, a sign of a field that has learned, through a century of hard-earned lessons, exactly how easily a genuinely interesting statistical pattern can be distorted into something far more alarming or far more falsely reassuring than the actual data ever supported. There is a broader lesson buried inside this entire 100-year investigation that extends well beyond the specific question of tides and earthquakes. One worth sitting with as we approach the end of this particular thread. Nature rarely reveals its patterns cleanly, all at once, in a single decisive experiment. It tends instead to offer faint, inconsistent hints, buried in noisy data, dismissed by one careful researcher, cautiously revisited by the next, refined gradually across generations of scientists willing to keep asking the same question with slightly sharper tools each time, even when the answer stubbornly refuses to resolve into something simple. To understand exactly why researchers today are so careful about how this tidal correlation gets communicated, it helps to look back at a specific, cautionary chapter in the broader history of earthquake prediction, one that unfolded in China during the 1970s and still shapes how seismologists approach public communication today. In February of 1975, Chinese officials made the extraordinary decision to evacuate the city of Haicheng based on a combination of unusual animal behavior, changes in groundwater levels, and a swarm of smaller foreshocks that seismologists at the time interpreted as a warning sign. Hours later, a major earthquake struck the region, and because the evacuation had already taken place, the death toll was dramatically lower than it otherwise would have been, becoming, for a brief period, one of the most celebrated successes in the entire history of earthquake forecasting. That celebration proved painfully short-lived. Just 18 months later, in July of 1976, an even larger earthquake struck the nearby city of Tangshan without any comparable warning signs being detected beforehand, killing an estimated 250,000 people in one of the deadliest earthquakes of the 20th century. The stark contrast between Haicheng's apparent success and Tangshan's catastrophic failure, occurring so close together in both time and geography, became a defining lesson for the entire field of seismology going forward. A blunt demonstration that even a genuinely encouraging set of precursor signals could fail catastrophically the very next time similar conditions arose, and that no forecasting method, however promising it appeared in one instance, could be trusted as reliably predictive without an enormous amount of additional testing across many more events than any single dramatic success or failure could ever provide. That hard-earned lesson sits directly behind the careful, heavily caveated language researchers use today whenever tidal correlation findings reach a public audience. And a second, more recent cautionary episode reinforced the same lesson even further. In the Italian city of L'Aquila, in the spring of 2009, a panel of scientists held a public meeting intended to address growing anxiety among residents following a swarm of smaller tremors that had been rattling the region for months. During that meeting, officials offered reassurance that the ongoing swarm did not necessarily indicate a larger earthquake was imminent, reassurance broadly consistent with the general statistical understanding at the time, since most earthquake swarms do, in fact, fade away without producing anything larger. 6 days later, a devastating magnitude 6.3 earthquake struck the city directly, killing over 300 people and leaving thousands more without homes. In the aftermath, several of the scientists involved in that public meeting were controversially charged with manslaughter, based on accusations that their public statements had provided false reassurance that discouraged residents from taking precautions they otherwise might have. Their convictions were later overturned on appeal, with the appellate court concluding that the scientists' actual statements had been reasonably calibrated to the genuine scientific uncertainty available at the time, rather than an irresponsible or falsely confident guarantee of safety. But the case sent a chilling ripple through the international seismology community, regardless of its eventual legal outcome. A stark reminder of just how much weight the public places on scientific statements about earthquake risk, and just how carefully researchers now feel compelled to frame any statement touching on the likelihood or unlikelihood of a future earthquake tidal correlation research very much included. This is precisely why, when researchers today discuss their tidal forecasting models, every single public statement comes wrapped in careful, repeated qualification, emphasizing exactly how modest the effect actually is, exactly how narrow the specific circumstances are where it has been documented, and exactly how much remains uncertain about whether, or how, it could ever be responsibly incorporated into any kind of public-facing, hazard communication. That caution is not bureaucratic hedging. It is the direct, hard-earned product of decades spent watching what happens when scientific nuance gets flattened into something simpler and more confident than the underlying data ever actually supported, in both directions, whether toward false alarm or false reassurance. This distinction between the carefully documented, narrowly scoped tidal correlations we have spent this evening walking through, and the broader, unsupported popular claims about supermoons and earthquakes that continue circulating despite repeated scientific testing, illustrates something important about how a genuine, if modest, scientific finding can become distorted once it travels far enough from the careful researchers who originally documented it. That same wariness explains the field's collective skepticism toward a very different, far less rigorous claim that has circulated periodically in popular culture for decades: the idea that a supermoon, the point in the lunar cycle when the moon's orbit brings it slightly closer to Earth than usual, meaningfully increases the risk of a major earthquake striking somewhere on the planet. This specific claim has been tested directly, repeatedly, by seismologists comparing historical earthquake catalogs against the timing of supermoons stretching back decades, and the results have consistently failed to show any meaningful increase in overall earthquake frequency or magnitude during these periods. The physical reasoning behind why is straightforward once you understand the actual scale involved. A supermoon brings the moon perhaps 10% closer than its average distance, a genuinely tiny variation compared to the much larger twice-daily tidal stress cycle that exists regardless of the moon's specific orbital distance on any given night. The same steady, rhythmic cycle researchers have spent the last century carefully studying in the far narrower, far more specific circumstances where it does appear to matter. The real story, patient, narrow, hard-won across more than a century of careful testing, is considerably less dramatic than the popular version, and considerably more interesting precisely because of how specific and well-earned its conclusions actually are. There is something worth carrying forward from both of these cautionary chapters. Heicheng and Tangshan on one side of the world, L'Aquila on the other, a lesson that shapes not just how tidal research gets communicated, but how the entire field of earthquake science approaches the delicate balance between genuine scientific humility and the very real human need for actionable information. Every population living near an active fault line deserves honest, carefully calibrated information about their risk, neither falsely alarming nor falsely reassuring, and striking that balance requires researchers to resist two very different, equally tempting shortcuts. The temptation to overstate a promising finding, because a confident, dramatic conclusion travels further and draws more attention than a carefully hedged one. And the opposite temptation, to understate a genuine but uncomfortable signal, because acknowledging uncertainty feels safer than risking the kind of backlash researchers faced after L'Aquila. Navigating between those two pressures, honestly, consistently, across every single public statement, is itself a kind of quiet discipline that rarely gets celebrated, but which sits at the very center of what responsible science actually looks like when the stakes involve real people living real lives above real fault lines. That same discipline is exactly what continues to guide how tidal triggering research gets discussed today, more than a century after a physicist first noticed a strange, uncertain pattern in a stack of earthquake records nobody had thought to examine quite that way before. Every new paper, every refined statistical model, every additional slow slip episode carefully logged beneath the Pacific Northwest, adds one more small, honest piece to a picture still very much in progress. A picture researchers are in no hurry to declare finished, precisely because they understand, perhaps better than almost anyone, exactly how costly it can be to mistake a promising pattern for a settled truth before the evidence has genuinely earned that confidence. That patient effort continues tonight, in seismology departments scattered across every continent, in research stations monitoring the ocean floor along volcanic ridges, in universities analyzing decades of tremor recordings from beneath the Pacific Northwest, in Japanese laboratories carefully testing forecasting models against the next major earthquake, whenever and wherever it eventually arrives. None of it moves quickly. All of it requires exactly the kind of quiet, unglamorous persistence that built this entire field from a single strange observation, more than 100 years ago, into the careful, nuanced, still unfolding understanding researchers currently hold about the surprisingly real, surprisingly narrow relationship between the moon hanging quietly overhead and the solid ground resting beneath wherever you happen to be lying right now. That quiet discipline, resisting both overstatement and understatement in equal measure, is precisely what has allowed this specific field to keep making genuine, if modest, progress in recent years, even while the broader public conversation around earthquakes and the moon continues to swing, as it always has, toward far less careful territory. It is worth spending these final few minutes together looking at where the research actually stands today, heading into the current decade, because the picture has grown noticeably richer and noticeably more precise than it was even a decade ago. Modern satellite technology has played a significant role in this recent progress, particularly a class of instruments capable of measuring ground deformation, with a precision that would have seemed almost impossible to the researchers who first proposed tidal triggering back in the 1890s. These satellites now allow scientists to track subtle, ongoing ground movement across entire fault systems continuously, rather than relying solely on scattered seismometers waiting passively for an earthquake to actually occur. Combining this continuous deformation data directly with tidal stress models has given researchers a far more complete, moment-by-moment picture of exactly how close specific fault segments sit to their own breaking point at any given time. Context that makes any subsequent tidal correlation considerably easier to interpret with confidence. Machine learning techniques have also begun quietly reshaping this field over the past several years, allowing researchers to sift through vastly larger seismic datasets than earlier statistical methods could realistically handle, identifying subtle patterns in tremor timing, migration, and tidal correlation across thousands of individual slow-slip episodes simultaneously. Rather than the smaller, more limited samples earlier researchers were restricted to working with by hand. Several recent studies applying these newer computational methods to the Cascadia tremor record have found the tidal correlation there to be even more robust and even more precisely characterized than earlier, simpler statistical approaches had originally suggested, adding further confidence to what was already the clearest documented case of tidal influence found anywhere on the planet. None of this recent progress has changed the fundamental, carefully bounded conclusion researchers have arrived at after more than a century of patient investigation. The moon's gentle, twice-daily pull on the solid Earth does appear to genuinely influence the timing of specific, well-identified categories of seismic activity, most clearly in slow-slip and tremor zones like Cascadia, and to a smaller but still statistically meaningful degree among the rare, largest earthquakes capable of cascading across enormous sections of fault. It does not meaningfully influence the vast majority of ordinary earthquakes people experience day to day, and it offers nothing resembling the kind of confident, specific prediction the public has often hoped earthquake science might one day deliver. Several research groups are currently extending this work into entirely new territory, applying the same careful methodology to subduction zones beyond Cascadia and Japan, including segments off the coast of New Zealand and Mexico, where slow-slip behavior has more recently been documented, and where researchers are eager to see whether the same clean tidal correlation holds up in a different geological setting, with different rock composition, different fault geometry, and a different history of past ruptures. Early results from these newer regions have been encouraging, showing correlations broadly consistent with what Cascadia first revealed, though researchers are careful, as always, to note that each new fault system requires its own independent, multi-year dataset before any conclusion can be considered genuinely reliable, rather than a hopeful early pattern that might not hold up over time. There is also a growing effort to understand tidal influence, not just in terms of whether it exists, but in terms of what it might eventually reveal about the deeper physical properties of the fault zones themselves. Because the strength of a fault's response to tidal stress depends heavily on specific frictional properties, how easily rock slides against itself under different pressures and temperatures, researchers have begun using the tidal correlation itself as a kind of diagnostic tool, working backward from how strongly or weakly a given fault segment responds to the tidal cycle to infer physical characteristics about that fault that would otherwise be extremely difficult to measure directly from thousands of feet below the surface. This represents a genuinely elegant scientific turn, transforming what began as a simple yes or no question, does the moon trigger earthquakes, into a nuanced diagnostic instrument capable of teaching researchers new things about the hidden mechanical properties of fault systems buried far too deep to ever study directly by any other means. Newer theoretical models have also begun exploring an even more subtle possibility: whether the tidal cycle might interact not just with individual slow slip events in isolation, but with the broader, longer-term rhythm of how these episodes recur over years. Cascadia's roughly 14-month cycle between major slip episodes is itself an object of ongoing study, and some researchers have begun investigating whether the precise timing of that longer cycle might itself be subtly influenced by longer-period tidal variations tied to the more complex, multi-year orbital relationship between the Earth, Moon, and Sun, a question considerably more intricate than the simple twice-daily tidal stress researchers first began studying, and one that may take years of additional data before a clear answer emerges either way. What all of this ongoing work offers, ultimately, is something quieter and, in its own way, more genuinely satisfying than a dramatic breakthrough ever could: a real, hard-won piece of understanding about how our planet actually works, patiently extracted from more than a century of careful, often frustrating research, built by generations of scientists willing to keep asking the same strange question long after it would have been easier to simply set it aside. It brings us back, in a way, to that quiet moment we began with: researchers checking the timing of the Tohoku rupture against the tidal stress acting on that fault, and finding, to their genuine surprise, that the two lined up almost precisely. That single moment did not solve the puzzle on its own. It reopened it, sending an entire field back through a century of old data with fresh eyes, leading eventually to Cascadia's tremor, to the volcanic ridges beneath the ocean, to the confirmed moonquakes shuddering deep inside our nearest neighbor in space, each discovery adding one more careful, hard-earned piece to a picture that is, even now, still not entirely finished. The moon overhead tonight, wherever you happen to be resting, is still quietly tugging at the solid rock beneath you, exactly as it has every single night for as long as the Earth and Moon have existed together. A gentle, rhythmic pull too small to ever feel, but real enough, in certain very specific corners of the planet, to leave its faint signature in the timing of the ground's own ancient, ongoing movement. Thank you for spending this long, quiet evening with us here at Pale Blue Drift. If slow, careful mysteries like this one are the kind of thing you enjoy drifting off to, there will be more of them waiting whenever you need them. Good night.